So let's talk about pH of acidic solutions and how you calculate pH. It's a very important calculation in acid-base chemistry. So for strong acids, it's very simple. Because strong acids completely dissociate, they all form ions. It's not an equilibrium situation, which means that it's very simple to find the pH. Okay, all it is going to be the negative log of the concentration of the acid, because all of the acid dissociates. This is assuming a monoprotic acid. Polyprotic acids, you have to multiply by however many protons you have. You'll see what that means. So we have a 0.10 molar solution of HNO3. HNO3 is monoprotic. It has 1 H plus for every molecule of HNO3. Since it's a strong acid, that means that it dissociates completely. The way we look at this is in figuring out pH is you write the important species when you're doing these problems. So for this one, we've got H plus, we have NO3 minus, and we have H2O. Okay, we know that water can be both H plus and OH minus, but very small amount, 1.0 times 10 to the minus 7th molar. That's so small compared to 0.10 molar H plus that we ignore it. Okay, so really the only important chemistry that's happening here is HNO3 is splitting into H plus and NO3 minus. For every one molecule of HNO3, you get one molecule of H plus, one ion of H plus. That means for every mole of HNO3, you get 1 mole of H plus. So the concentration of H plus is the same as that of the acid. Take the negative log and you get pH at 1. Okay, so for strong acids, you don't have to worry about ice tables or Ka values or any of that stuff. All right. So what about this one? Find the pH of 1.0 times 10 to the minus 10th molar HCl. Very small concentration, right? HCl splits into H plus and Cl minus, but the concentration of H plus is so small, it's actually less than water. It's less than water's concentration of H plus, 1.0 times 10 to the minus 7th. So water's contribution to the hydrogen ion concentration is greater. So I can ignore the HCl, and it's just going to be the negative log of 1.0 times 10 to the minus 7th, which is 7. Okay. Now for weak acids, it's different because weak acids don't completely dissociate. Their equilibrium generally will lie pretty far to the left. And since they're at an equilibrium position, that means we're going to have to use an ice table, right? Again, you want to write the major species involved, and you want to consider which species contributes the most to H plus concentration. Okay, and then you make an ice chart, you use your initial concentrations, you figure out your equilibrium concentrations, you put your equilibrium values in a Ka expression, you solve for X as usual. Okay, now you can use the approximation rule here, but again, you want to check to make sure that the value of X is less than 5% of the initial concentration of that acid. Okay, we did that before in the last chapter. And then you find your pH. Okay, so here's an example. We have a 1.00 molar solution of HF, which is a weak acid. The Ka value for HF is 7.2 times 10 to the minus 4th. All right. The two species that can provide H plus ions are HF and H2O. Okay, HF can form H plus and F minus. H2O can form H plus and OH minus. All right. The value of Ka is 7.2 times 10 to the minus 4th. That's a very small value. And if you think about it, the value of water's Kw is 1.0 times 10 to the minus 14th. Given these two numbers, it's pretty clear that water is not going to provide a whole lot of H plus in this example. It's going to be the Ka, the HF rather, that gives the H plus. So I'm going to ignore the water's contribution. Here's my ice table. HF going to H plus and F minus. My initial concentration of HF is 1 molar. I have no H plus and F minus initially. Some of the 1 molar is going to decrease. Some of the H plus will increase by the same amount and F minus by the same amount. And so my equilibrium expressions are 1 minus X, X, and X. Plugging that into my expression for Ka, this is just an equilibrium problem. We solve for X. We can approximate 1.00 minus X as just 1.00 as long as X is small enough. And we would have to check that approximation. X comes out to be 0.027. And so if we check 0.027, we are going to divide 0.027 by the initial concentration of the acid. 1 times 100 is 2.7%. So yes, our assumption is validated. Okay. So the concentration of H plus is what X was. So we just take the negative log of that and we get a 1.57 for our pH. Okay. Here's another example. 0.100 molar solution of HOCl. Ka for that is 3.5 times 10 to the minus 8th. Okay? Those are the two species, HOCl and H2O. HOCl provides a lot more H plus than H2O because its Ka value is much larger than the Kw value for water. So there's my ice table. 0.100 minus X, X, and X. Both are, this is a monoprotic acid, so both values will be X there. Plugging it into the equilibrium expression, making the approximation, we come out with X is 5.9 times 10 to the minus 5th. Check the assumption. 5.9 times 10 to the minus 5th over 0.100 is 0.059%, much less than 5%. And so our assumption is valid. So my X value is the concentration of H plus. Take the negative log of that, you've got 4.23. It's really not that difficult if you follow the steps. Do it in little steps. Okay? What if you have mixtures of weak acids? You've got a couple of weak acids mixed together and you want to find the pH. Well, then you have to figure out which one is the strongest of those. And you can do that by looking at the Ka value. And you can figure that out. And then you use the equilibrium values from that to use as initial concentrations for your weaker acid. Okay, so it's actually a two-stage equilibrium problem. We'll do an example. You'll see what I mean. So we have a mixture of 1.00 molar HCN. Ka value is 6.2 times 10 to the minus 10th. That's a very small Ka value, very weak acid. And 5 molar HNO2, which has a Ka value of 4.0 times 10 to the minus 4th. That's a much stronger acid than HCN. Okay, so HNO2 is the more important one that provides more H+. It has the highest Ka value. So I plug in. It's still a weak acid, but it has the highest Ka value. Okay, plug in 5 molar, 0 and 0, minus X plus X plus X. As usual, 5 minus X, X and X. Plug it into your expression, make the approximation. We're going to assume that X is much smaller than 5 molar, right? And it's smaller, reasonably smaller, 0.045 molar. We still have to check our concentration, okay? But we'll do that later. We now use that value for H plus as the initial concentration for the HCN dissociation. So HCN was 1 molar to start with, but we already had 0.045 molar H plus in solution from the HNO2. We had no CN minus. Use your change again is minus X for the HCN plus X for the H plus and plus X for the CN minus. We get new equilibrium expressions. We plug into our expression for Ka for HCN. Okay, we can make the approximation again because we're assuming the Ka value of HCN is so small that X is going to be tiny compared to 1, which is what we're subtracting it from. So we can make the approximation again. Okay, and that gives us a value of 1.4 times 10 to the minus 8th. You don't even have to do that. You can look at, compare 1.4 times 10 to the minus 8th to 1.00. It's obviously less than 5%. Okay, you can check it to be sure if you feel like you need to. All right, so now I add those two together. The concentration of H plus from the HNO2 was 0.045. The concentration of H plus from the HCN was 1.4 times 10 to the minus 8th. You add those together, the 1.4 times 10 to the minus 8th is so small, it does nothing. It's negligible. So the concentration of H plus is just 0.045. Take the negative log, you get a 1.35 pH. Okay. What is the CN minus concentration at equilibrium? CN minus is actually a conjugate base, right? It's the conjugate base of the weak acid HCN. And back earlier we learned that a strong conjugate base is formed from weak acid. Okay, so our concentration of CN minus is 1.4 times 10 to the minus 8th. Okay, which is how we found it. This is the same calculation we did before. Now, percent dissociation. This is we talked about this as saying that weak acids don't completely dissociate. Strong acids do, but weak acids don't. Weak acids only ionize or dissociate a little bit. So we can calculate how much by using the percent ionization or percent dissociation calculation. It's the amount of the acid dissociated divided by the initial concentration times 100. Okay? Very simple. For weak acids, as the concentration of the acid increases, as the molarity increases, the percent dissociation goes down, and vice versa. Okay? As you dilute an acid, you decrease its molarity. Okay, as you dilute it. that causes the equilibrium to shift towards the side with the greater number of particles, which is the right side of the equilibrium, which means you're going to dissociate more acid as you dilute it. Okay? This is just a graphic that shows you that. So if we want to calculate percent dissociation, it's very simple. The first thing we need to know is how much of the acid was actually dissociated. What was the actual concentration after dissociation? So we have 1.0 molar acetic acid. There's your Ka value. It's still just an ice table calculation. We're looking for X. Okay? We plug that into our expression. We make the approximation. We find that X is 1.8 times 10 to the minus fifth. Sorry. We make the approximation. We find that X is 4.2 times 10 to the minus third molar. Okay? The amount dissociated divided by the initial concentration. Well, the amount dissociated is 4.2 times 10 to the minus third. That's how much disappeared. That's how much of the acid went down. Remember, it was minus X. And over the initial concentration, 1, so 0.42%. It's the same calculation that you would do to check the approximation. We'll tell you the percent dissociation. So make the connection, right? Weak acids, the approximation works for weak acids as long as they're less than 5% dissociated. So our percent dissociation is 0.42%. All right? What about for 0.100 molar CH3COOH? Try this one on your own, and we'll check your answer in class. All right, what about going the other way? I have a 0.200 molar solution of some weak acid, and it's dissociated 2.5%. Find the Ka of this acid. We're going to go backwards. Okay, so what do we know? Well, we know that the amount dissociated over the initial concentration is times 100 is 2.5%. So the amount dissociated is what we're looking for. That's our X value. Over our initial concentration is 0.200 molar. That means our X value is 0.0050 molar. All right, well, what do I do with that? That's our X value. Well, we set it up our initial ice table if we were looking for its the calculation, right? It would be 0.200 molar, 0 and 0, and then minus X and plus X, etc. And we plug in our values. But we now know the value of X. It was 0.0050. So we just plug that in. We have our expressions at equilibrium. We plug in our value of X, and we can calculate our Ka value. So it's just going backwards. First you find X, then go backwards to Ka. Still need an ice table, but it's just a regular old ice table. So these calculations of pH take a little practice, but they're nothing more than just equilibrium problems. They're done the same way. So get to know the ice table. It's your friend.